Professor Sarawagi researches in the fields of databases, data mining, and machine learning. Her current research interests web information extraction, data integration, graphical models, and structured learning. She is an associate professor at IIT Bombay. But to that, she was a research staff member at IBM Almaden Research Center. She got her PhD in database from the University of California at Berkeley and a bachelor's degree from IIT Kolkata. She has several publications in databases and data mining, and she has several best ratings. She serves on the board of directors of ACM Security and VLDB Foundation. She was program chair for the ACM Security Conference 2008, research co-chair for the VLDB 2011 conference, and has served as a program committee member for Security, ICD, and ICML conferences. She is on the editorial board of ACM TODS, ACM TKDD, and FNT for machine learning journals. Now I ask Professor Sarawagi to start his talk.
Hello. Yeah, see, actually I cannot hear audio from your side. Hello, good morning everybody. Welcome to this talk on structured learning and graphical models. These are two very important tools for various kind of text analysis applications which arise in classification, information extraction, for example in part of tagging, name entity recognition, parsing, machine translation, social networking. This talk is mostly of the tutorial flavor in the sense that we describing sort of almost in a teaching mode graphical models and structured learning, and there will be a little bit of discussion of applications. And unfortunately, because of the limitations of technology, I will not be able to hear your questions unless Partho calls me. It's going to look more like a monologue, but sort of interrupt through Partho if you do not understand something. So now I'm going to share my slides with you. So first I'm going to talk about graphical models, then in the second half we'll talk about structured learning. Okay, so graphical models or probabilistic graphical models, these are a very important and core tool for text applications. So here the basic problem is as follows. You are given several variables. Denote all throughout this talk the variables as x1 through xn, and the basic premise is that n is very large, and your goal is to build a joint distribution function over this very large number of variables, and we are going to call this probability distribution function as PR x1 through xn. And after you have created this distribution function, we want to use it for answering several kinds of projection queries on the distribution. So the typical kind of queries that we are interested in will involve, for example, marginals over a small set of variables, like say 1 or 2 variables, or questions about the maximizing point of the distribution, which is the mode of the distribution. And the whole reason we are interested in graphical models is that n is very large. So representing the joint distribution over this very large number of variables explicitly, say for example using a truth table, is not at all an option. Our only hope is to come up with some efficient representation which can also be queried efficiently. So I'll start with an example to make our discussion more concrete. Let's say we have a database of people, and people are described by these 5 variables: age, which let's assume we have discretized into 10 ranges; income, which is again discretized into some 7 different scales; the number of years of experience a person has is discretized into 7 scales; the highest degree of the person, and the location where the person is working. So this is like a payroll data of a company. So we are interested in using this huge database about people and their 5 attributes to understand, for example, what are the fraction of people whose highest degree is PhD and whose salary is say less than a certain amount. So these are examples of projection queries that we would like to answer without actually representing the fraction of people corresponding to all possible combinations of these 5 attributes value. So if you look at the number of possibilities that would arise, it would be 10 possible age values times 7 possible income values, 7 possible experience values times 3 possible degree values times 30. That will be 44,000. Small number based on modern computing infrastructure, but this is just a toy example to sort of help us understand graphical models. So now if you try to, so I just mentioned that explicit joint distribution you don't want to use. So the natural other option to consider is to see if these variables are independent of each other. Now if you try to check whether these variables are independent of each other, you will find that age, income and experience, at least these are all highly correlated. So and also degree and income are correlated. So you find that if you try to use the independent assumption to reduce the space required to represent the distribution, you might be incurring a huge approximation error. So what are the ways in which you can simplify the distribution? So the whole point of graphical models is that when you are starting out with probability and statistics, you kind of only think in terms of independence and lack of independence. So basically whether 2 variables are independent of each other or whether they are correlated. But when you consider sets of variables which are of size greater than 2, then there is a notion of conditional independence which is very useful in simplifying the representation distributions over a large number of variables. So if you consider this example, you will find that income is not independent of age. Sorry, I have not introduced this notation. I am going to use this notation to denote lack of independence when it's crossed, otherwise it's independent. So income is not independent of age, but when you look at the conditional independence property, then you find that income does become independent of age once you account experience. So the income is independent of age given experience. So graphical models provide us a visual way to represent such conditional independences and to exploit these conditional independences for efficiently answering several kinds of projection queries. Sorry. So graphical models are an intuitive way to represent and visualize joint distributions, and they represent the distribution as a graph which expresses the conditional independencies which hold among sets of variables, and then they quantify the distribution through potentials hold over subsets of variables. And the second point is that the representation is such that you can query this joint distribution efficiently for various kinds of subsets queries on the distribution. So graphical models can be thought of as a combination of graph theory and probability theory. Graphical models have a long history. Perhaps many of you in the audience are already familiar with this technology. So they have roots in statistical physics, where they were used earlier for modeling the interaction among atoms in solids. Independently, in genetics also, graphical models, more the directed counterpart of the graphical models, were used for studying the propagation of properties among species. Then later, in specifically more in computer science, graphical models were first used in expert systems. But now there are, of course, applications all over. In a lot of the research that we do in our group on areas web search and structure extraction and information extraction problems, almost all of them have some or the other form of graphical models used within the core analytic engine. So there are applications, for example, the cell phone that you're holding is using a graphical model inference algorithm to do error correcting codes. In robotics and vision, graphical models are used, for example, image segmentation, or interpreting depth in stereo vision. These are all problems which are solved through various kinds of graphical models. In text mining, as I just mentioned, which is the focus of this workshop, there are many applications of graphical models. And in fact, I will be elaborating on some of them in the second half of the talk in bioinformatics and in data mining. So now, so that was just an overview of graphical models. So now I am going to actually go into pure tutorial mode and describe details about graphical models. First we will talk about how to represent graphical models, how do the graph structure, conditional independencies, and factorization of probability distributions interplay to allow you both efficient querying and efficient storage of large probability distributions. Then I will talk about answering inference queries on graphical models, and then we'll talk about how to construct or learn a graphical model, and then we will talk about structured learning. So that will take us to the end of graphical models, and then we will talk about structured learning and training of structured models. Let me just take a small sort of break here and ask you if you have any questions. Any questions? Okay, let's continue then.
Yes.
So now, as I mentioned earlier, there are two kinds of graphical models. Directed graphical models, which are also called Bayesian networks, and undirected graphical models, which are also called Markov random fields. So in a graphical model, there are two parts. One is the graph, which qualitatively expresses the dependencies among the sets of variables whose joint distribution you are trying to represent, and the other is the potential, which quantifies the distribution. So the graph, to start with, consists of nodes. So for each of the n variables, you have a node. So suppose you are trying to represent the joint distribution over n variables, you will first start off by creating n nodes in a graph. But the edges have to be created in a very stylized manner. They are somewhat non-trivial, and they depend on whether the graph is directed or undirected. And the variables themselves can be either discrete or continuous. Although most of the examples that I'll be mentioning will be with discrete variables, Almost all of the technology of graphical models apply equally well to continuous variables. So you could have a variable like a temperature in a room, or the income, instead of it being discretized, could be a continuous variable. And then the edges. So you will. So the one very simple rule to state about edges is that anytime you have two variables which cannot be made conditionally independent, no matter what other variables you keep in the conditioning set, then you would have a direct edge between these two variables. So that is a very simple rule that applies to both directed and undirected graphical models, but that's only a one-way rule, and we will know more about what the edges mean later. Okay. I have a call from partners, so I will take this call. Hello. So this is what I was saying, that in the graphical model, there are two parts: the graph, which qualitatively represents the distribution, and the potential, which quantifies the distribution. So the graph, the nodes in the graph are easy to specify. For each of the n variables, you will have a node in the graph. And the edges will be directed in a Bayesian network and undirected in a Markov random field. And the semantics of what the edges mean and when you add those edges, that we will go to shortly. Okay. So now, the potentials, these are defined over subsets of variables. Now, which subset you define together, which subsets participate in a potential, and what do the potentials mean, and how do they give you an overall distribution, that I am going to also describe separately for Bayesian networks and MRFs, Markov random fields. Okay. So, but the important thing is that once you have potentials defined for a graphical model, the joint distribution over the n variables is a factorization over the potentials. So essentially, the first thing that we learn about a graphical model is that it represents the joint distribution over various variables as a product of several terms, where each term involves a small subset of variables, ideally. Okay. So because of this factorization, you are able to represent the distribution efficiently, and also you can imagine that one can then exploit this factorization to do efficient querying over the distribution, efficient projection operations on the distribution. So now things will be more clear when I describe each of the Bayesian networks and MRFs separately in terms of what the edges mean, what the potentials mean, how do the potentials give you the joint distribution. So first we'll talk about Bayesian networks. Bayesian networks are directed graphical models. A Bayesian network has one condition, which is that the graph has to be acyclic. You cannot have cycle in the graph, and of course all the edges are directed. Now, because the graph is acyclic, you can go ahead and define a notion of parent-child between sets of nodes. So first we'll define the notion of parents of a node. So you have a directed graph. So the parents of a particular node xi is just the set of nodes in the graph which are directly pointing to xi. Okay? And then we can define potentials. Once you have defined the parents, now we can say that in a Bayesian network, the potentials have a particular meaning. So for every variable I, you have a potential over that variable xi and the parents of xi, and the potential is just the conditional probability of xi given the parents of xi. Now, once you have these potentials, you can claim that the joint distribution over the combination of variables is just the product over the probability of each variable given the parents of that variable. So as long as you have created a Bayesian network where for a variable the set of parents is small, you will have an efficient factorization of the distribution. So let's go to our example earlier of this people database where we have 5 variables. We have location, age, experience, degree and income. And just based on our knowledge of real life, we can try and construct a directed graph to represent this joint distribution. For example, it is natural to assume that the income of a parent, of a person, is determined directly based on the degree and experience. Even though income is correlated with age, income becomes independent of age given the amount of experience that a person has. And of course, the experience that a person has depends on how old a person is. Generally, older people will have more experience than younger people. So that's why we have a direct edge from age to experience. So most of the Bayesian networks in operations are created like this, in the sense that a domain expert interprets the variables and adds edges between those variables where one directly affects the other. But of course, you would also like to be able to learn such Bayesian networks automatically given large samples like what we do in typical machine learning. And there are, of course, many algorithms for learning such graph structures, and we will discuss those later. Currently, we are only interested in understanding what the graph is telling us. What are the set of conditional independencies which the graph is expressing, and how do we exploit those conditional independencies to simplify the distribution and to answer queries efficiently. These are our twin goals for this part of the talk. Okay, so this is the Bayesian network, and now given this Bayesian network, now let's try to quantify the distribution. So from just this graph structure, we are able to understand qualitatively how the variables affect each other, but now we want to quantify that. So we will quantify that through potentials. The first potential we will define is over the variables which do not have parents. So location, for example, does not have parents. So the potential corresponding to location is just the marginal probability of location. So here is an example. Say suppose if you have a database of people where the set of seen locations are these 4 locations, then this could be a marginal probability table that you will store as potentials. Again, how those values were obtained, 0.2, 0.3, 0.1 and 0.4, this is going to be again obtained through some learning exercise. And here we are not sort of worried about how those potentials were obtained. We just want to understand what the potentials mean. Okay. And then this is age is another variable without any parent, so its potential will just be probability of age. And since I mentioned earlier that I have discretized age, then for each possible discrete label of age, I will store a probability distribution. But suppose if I had not discretized age and if I had represented that as a continuous variable, then I could define any continuous distribution as a potential. For example, I could have chosen to represent this potential as a Gaussian distribution, and then the potential would just have the parameters of the Gaussian distribution, which would be just the mean and variance of the distribution. Now we get to other variables, like say if we consider this variable experience. For this variable, the potential is probability of experience given age, because experience has this one parent age. So this is a conditional probability table, CPT in short, that we will have to store. So here we have for each value of age, so suppose if you consider age group 20 to 30, for each value of age, we will have a full distribution over experience. So experience is over the columns. So you will find that all the rows have to sum to 1 because they are supposed to represent a distribution over experience. Okay. And then we have this last potential. No, there is another potential over degree, which I have dropped here for space issues. And then for income, there are 2 parents, probability of income given degree comma age, and this is going to be a 3-dimensional CPT. Now this will already, it is sort of somewhat cumbersome than representing a 2-dimensional table, so we have not explicitly represented here. And but from here you kind of should get this message that if you want to create an efficient Bayesian network, you want to minimize the number of parents that a variable has. And once you have these potentials defined, now you can go ahead and define the joint distribution over these 5 variables as a product of these 5 small conditional probabilities, and you can do the math and you will find that the number of parameters that you will have to store in this simplified factorization of the distribution is much smaller than what you had if you used the full explicit. For that we had around 44,000 parameters to store, whereas here it will be much less. Okay, so now we understand a little bit about what a Bayesian network means and what do the directed edges tell us in terms of the factorization of the distribution. But the other advantage of using a graphical model is that it also expresses qualitatively conditional independences among subsets of variables. So now, both for Bayesian networks and for MRFs, one important topic for us is how to read off the conditional independencies which a graph is expressing. Now, the reading off of conditional independencies for the case of Bayesian networks is somewhat more involved than for the case of MRFs. So let me go through them. First, for the case of Bayesian networks, I'm going to use this notation of capital letters to denote sets of variables. Suppose if I have 3 sets of variables, capital X, capital Y, and capital Z, then we will claim that X is conditionally independent of Y given Z in this notation as X conditionally independent of Y given Z, if and only if probability of X given Y comma Z is equal to probability of X given Z. So the first important result for a Bayesian network is this rule that you see here. It says that every variable xi is conditionally independent of this new term I have introduced, ND, for it's a short form for non-descendants. So every variable xi is independent of its non-descendant given its parents. So the parent kind of shields the variable xi from other variables which are not direct children or grandchildren of xi. So we'll go through an example. If you look at this 5 variable Bayesian network, then for each xi, so if I take location has no parents. So in the conditioning set, I have nothing, it's an empty set. But none of the 4 variables are descendants of location, so they are all non-descendants. So we can claim that location is conditionally independent of the set Y consisting of these 4 members, experience and using the short form D for degree, similarly E for experience, A for age, and I for income, and L for location. Then you come to age. Age again has no parents, so the conditioning set is empty, and the variables experience and income are descendants of age, but location and degree are not. So we can claim that age is conditionally independent of location and degree. Now you come to experience. Experience has one parent, age. So in order to use this rule, we have to say experience is conditionally independent given age of the non-descendants location and degree. If you go to income, income has 2 parents, experience and degree. So we will say that income given experience and degree is independent of its non-descendant, and the only non-descendant, actually we have 2 non-descendants here, age and location. I dropped location. Location also should be in this set. So income is conditionally independent of age comma location given experience comma degree. So so based on this rule, in fact, we can show that. So first let me define something. So this rule that that I have mentioned that every variable is conditionally independent of non-descendant given the parents, this rule has a name. We are going to call it local CI. CI is short form for conditional independence. So we want to say that this is a local conditional independence rule. And the interesting thing is that if you just start with this rule, that every variable is conditionally independent of non-descendants given its parents, then you can derive the factorization formula that I mentioned earlier. And the proof of this is so simple that let me go over it. First, since we started with the assumption that the Bayesian network is acyclic, we can assign a topological order of the variables in the directed graph so that parents always have a smaller number than their children. So without loss of generality, assume that x1, x2 through xn is such a topological sorting over the n variables. Now, we know from local conditional independencies that each variable xi, given all the variables before it, can be this conditional probability is going to be just equal to the probability of xi given the parents of xi. Why? Because any variable which appears before I, okay, it's either the parent or it is a non-descendant. If it is a descendant of xi, then it will necessarily have a higher number. So because of the local CI rule, since xi is independent of its non-descendant given the parents, we can say that probability of xi given x1 through xi minus 1 is equal to probability of xi given the parents of xi. So this is first condition. This is one result that we have, which is directly implied from the local CI rule and from the fact that the graph is